The previous video we looked at wide streaming and how that's actually slightly different, rather significantly different in terms of use cases from batch. Here, let's start looking at what makes streaming a different kind of a problem statement. So, the streaming context is one of machines talking to each other, one of automation resulting in data processing. It's very rarely meant for humans. So, allow me to explain. In the use cases that we spoke about in the previous video, we saw that there were some examples where machines have to process data and decide whether something is abnormal, right? Like the payment example, or something needs to be acknowledged immediately. Sorry, the abnormal stuff was regarding the cards, right? The cards being used in a location or in a pattern that's not right. That's not normal for you as a card user. So where the machine is dictating or rather deciding whether the card is being used in genuine fashion. The other example was payments, where it was important that the machine immediately acknowledge the payment that was made and make the appropriate booking in the backend system. So again, that's machine driven. The last example that we saw in the previous video was a customer who's about to buy but needs clarification, so he wants some interaction with an expert. Even in that scenario, where it's a human that desires a human touch, the act of figuring out that the human requires a human touch is actually a streaming job that gets done using automation. So it's a machine that continuously processes that customer's browsing behavior and the purchasing behavior, and at the right point makes the intervention and says that, look, there's a need for an expert to reach out to this individual. Okay, so until that point, it's all completely automation driven at very, very large scale. Right? It's impossible for a human to consume that kind of a scale and that kind of a velocity. So the machine is doing that. And once the machine gets its job done, then it alerts the human to say, I think you should talk. If the machine was not doing its job well, then you would need probably like 100 to 1,000 times as many number of people today to monitor and make these dimensions. Otherwise, you would not be able to deal with that velocity of data. Right? So the machine is doing a very critical role of streaming processing so that the humans do not do that, so that the humans can only focus on the interactions that actually result in business. So that's what I mean by when I say streaming is very rarely going to be about humans consuming streaming data. Maybe the video example is the one odd example, right? Where you're continuously consuming live video, and that's just video processing. There is no data processing, there is no data science in real time, none of that. It's just a very standard video encoding problem. Here, for the most part, we're talking about applied data science, we're talking about data engineering, we're talking about thresholding, and those kinds of problem statements are fundamentally about machines acting on the data. Yeah, so I guess I've delivered the point here. So a streaming context comprises of multiple different parts or components to the stack. At the topmost layer, you have the application itself, which is responsible for coding up that particular business logic. Like in the case of IRCTC, this is the ticket reservation system coupled with the payment processing system. So once the payment is processed, then it hands off to the ticket reservation system, which then makes an entry, like we spoke about. So then the application here comprises of all the different modules that IRCTC has, especially the payment processing system. And usually, when a specific streaming event or streaming application is being designed for streaming events, there is always going to be some kind of a state associated with that context of where the particular customer is in the business process, and that state is critical in order to make the correct call, right, from a streaming perspective. So again, go back to the IRCTC example. If I need to make a payment for a specific booking, obviously I need to know what the booking is about. I need to know which train, how many tickets, who are the passengers, whether the senior citizen discounts applicable, armed forces discounts applicable, etc., etc. Apart from that, there is also this running state of the the time it's normally going to take for a payment to be made, and for that time duration, the ticket that you've made a booking for is blocked for you, right? So therefore, that ticket blocking is a state that gets that's part of the real-time application. The second angle here is there is a timer that's attached to it, right? There's a timer within which before it exhausts further, you have to finish your payment. If you don't do that, then your block on that particular set of tickets is lost. Then somebody else can book those same tickets. So that's also state, right? So the state usually is very closely tied to the application. That's why I've drawn it out as one box, but it's still a logically separate entity from the application. So the state dictates how you deal with the current data. The state gives you the context for the current data when it needs to be operated on. Alright, so the data itself is of course a separate component. Here we're talking about not just the data for that particular application, but also the data from the ecosystem, right? The data that's giving you additional flavors and contexts to the current event that you're processing. So this is a big departure from the traditional way in which data processing, especially in streaming, has been happening. A lot of streaming related use cases were very focused on a specific data set at a particular point in time. Like the payment processing example, it's only about payments, it's not about anything else, right? But increasingly, especially with the penetration of digital and the use of e-commerce for various businesses, it becomes evident that you need to think about all kinds of data, not just the direct data of the payment and the buying behavior and the purchasing, but you need to start thinking about the data from demographics point of view. Which customer, what is the product they're buying? Is the product conducive for, is the product amenable to fraud, or cheating or cash on delivery issues? Then you also need data about, like I said, the timer, right, which dictates basically whether you get this much amount of time for making the payment. If you don't make the payment within that time, it releases the reservations. So, etc., etc. All kinds of data start coming in, and those data sets become very essential for the application that's making a decision to get the complete context, right? Get the complete context of all the things that are happening in the business process. So that's data. Then you also need a stream processing software. This software is actually going to be the one that's responsible for ensuring that whatever data gets assimilated, accumulated, gets processed in real time, and the appropriate state gets updated and the application gets informed about it. So the stream processing software is where the magic is, effectively. Now, the stream processing software, it by itself does not store data. It only makes the computations possible. Usually the data gets stored in a separate system. Now, you could think that I could just get file system on a regular machine and put all the streaming data there, but the classic file system semantics is not conducive for streaming data, because firstly, the streaming connotation is that the data is not bounded, right? It just keeps coming. It's not as though somebody says, hey, this is my end of data, this is my end of file, when we close the file and then the file becomes available then for reading. Here, there is no such thing. You don't have like an end of file, you don't have a bound to the data. The data just keeps going, right, over a period of time. So that kind of a setup, if you start monitoring, rather if you start collecting the data in a monitored system like an operating system, which is controlling the file system, then you would not be able to close the file ever, right, because there's no bound. So therefore, classical OSs and file systems are not the right place for storing streaming data. What could be the right place is something that allows you to grow over a period of time, something that gives you a handle of the type of data that gets, the accumulation of data over the period of time, and also tells you like what is the current data set that's coming, what's the historical data that's been around, and what do we do with it, right? So those are all such considerations that this storage system for streaming data comes into play. So I call it persistent store software. There are many different variations for the technologies available to do this. So for instance, message buses are a very good example. Message bus is like a first in first out queue, right? It just keeps pushing ahead the data that's the oldest, and newer data keeps getting added appended to the end. And in this kind of a setup, it's very easy to reason about how do you deal with data processing, because you know exactly the order in which the data was actually produced. So yeah, so that's an example. But in general, we're talking about like a persistent store setup, and that setup is required for the stream processing to actually work. And then finally, of course, the compute, the data, all of that runs on hardware, and the hardware is closely associated with the velocity of the data that's coming in. So that's also part and parcel of the streaming context. Okay, so within the stack that I've just highlighted, the key questions that play a role as to how effectively you write the streaming program is the set of semantics at the application level, right? And that dictates, the semantics at the application level dictates how you go about architecting your entire tooling, right? Architecting your entire software. So first and foremost, do you need all the data all the time? Or do you need all data some of the time? The rest of the time, it's okay that you don't get all of the data? Or are you really saying that I don't need all the data all the time? In fact, I don't even need all data some of the time. It's perfectly alright if you give me most data all the time, right? And each of these three have very different meanings and have very different use cases also. So what does this really mean, right? First and foremost, it refers to the fact that the velocity is high, and therefore, if you happen to miss certain records, what do you do about it? You play it again, or do you just go on and say that, look, for my application, I don't need the data. It's stale. I shouldn't have missed it. That's okay. So I've missed it, so I don't need to go back to it again. Let's move on to the next data sources. That kind of a setup, you're getting most data all the time, which means some of the data you missed out, you're not going to get access to that, right? There are other kind of scenarios where you absolutely need the guarantee that you're getting all the data all the time. Like if you look at one of the use cases in the motivation slide, payments processing, like or financial transactions, credit card transactions, etc. In those kinds of setups, absolutely you cannot afford to lose any data, which means you're getting all the data all the time, and you need to do something about it. In fact, guaranteeing that all the data all the time is getting processed itself is a pretty hard guarantee, and we'll take a look at why that's the case a little later in this week's lectures. Now, all the data some of the time means that as long as certain things are happening, I'm going to get all the data. What kind of things are we talking about? Like lack of failures, the node continues to be up and running, the power is available for the nodes to actually keep making these big computations for streaming purposes, right? It could also be the case that the source provider is not available by themselves, right? They keep failing every now and then. But whenever they don't fail, they actually provide you all the data, and that's necessary for you to be able to, make some judgment calls and adjust the processes itself. Yeah, so that's all data some of the time. Most data all the time is when you are struggling for data processing bandwidth because you don't have enough compute power. The data just keeps growing over a period of time, and so at some point your data starts to drift, right? The data processing starts to drift, and in that case, to come back and regain from the drift and make it back to zero in terms of latencies, it's better that you just actually sacrifice some of the data all the time, right? So that you process most of it. It's still giving you a guarantee like 95-96% is something that you are able to process, but the remaining 4% or 5%, you defer it consciously, or you just don't process it at all. And that's applicable for certain use cases, like for instance, weather data, stock market data, etc. Right? So application semantics plays a key role in determining the resilience. So here the resilience comes down to the fact that how do I deal with changes to the tickets column. So what that means is